Hey mechanics students, how I got the best darn scoop for you. I've been trying to come up with the latest and greatest story, and I decided I would do an expose on shear stresses. Yeah. So I got a lot of interesting facts here. So I asked around and I've asked, how do shear stresses make you feel? And so one person said they're all cut up about it. Another student said, well, okay, I guess. And another student here said shear stresses make them anxious like other stresses. Yeah. Okay, I guess shear stresses are something that makes us anxious. Maybe we should investigate them a little bit further. I asked another question. What would you do to get rid of shear stresses if you were in charge? So one student said quarantine them. Not a bad option. But shear stresses are hard to see, and I don't know how we're going to quarantine them if we can't even see this thing going around. So I like the other student, though. The other student said we just have to deal with them, right? Like everything else, if you're in charge, you got to deal with shear stresses. So I think this is great. So far so good. This whole scoop is coming along great. But I thought we might need a little bit more facts than that. So I'm going to go ahead and send you over to the learning objectives to get some layout for what we're in store for. What an awesome set of learning objectives. We got 5 of them to do today. We got to hurry through them. First, illustrate the development of shear stresses in the cross-section. Then we'll derive the equations for transverse shear stress. Then apply the transverse shear stress equation to solve some engineering problems. Fourth, we'll generalize the equations to calculate shear flow. And lastly, use the shear flow equation to solve some engineering problems in composite beams and thin plate cross sections. Whoa, that's going to be a lot of stuff, but shear stresses, they're so beautiful. I'm ready to expose them in the beams. So when we talk about stresses in beams, we know that beams have transverse loads. Transverse loads leads to both shear and moment, right? We draw diagrams for both of them. Then we recall from a few classes ago, we calculated bending stress. The equation was sigma equals my over I. So we know how to calculate bending stress, but how do we calculate shear stress? That's what we need to learn. Go! Welcome back. I hope you're ready for shear stress day. Hopefully you remember all that other previous information. If not, you should go back and read it again. It's bending stress, right? Bending stress formula is my over I, or we remember as my eye. Oh, that movie just always brings back great sentimental feelings. But we don't have time to talk about lost fish and their forgetful friends today. We got shear stresses to deal with. Shear stresses, peoples. So hurry up, get into it. We're going to have to derive some sort of formula if we're ever going to hope to calculate this thing. So hop into the derivation right now. Go, do it. So this is going to be the derivation for the shear formula. In most cases, for long, slender beams, the amount of cross-sectional distortion is minimal, so warping stresses can be neglected. Great. All right, let's consider a beam with some arbitrary uniform load on it, all right? And I want to consider some portion, dx, a little slice of segment dx, and I'm going to do an arbitrary beam cross-section and an arbitrary loading, and I'm going to consider just that portion dx, and I'll go ahead and sketch dx shown here. Dx is going to be into the page here on this little block, this little chunk, this little wedge. All right, so I haven't applied shear force down. How am I going to resist that force in my cross-section? Well, I have little forces in my cross-section. These are going to be stresses. The stress is going to be smeared across the area of the cross-section, right? Force over area gives us stress. So the stress is smeared across this cross-section. And so I have a bunch of these little stresses, right? These little stresses are going to be our shear stress, tau. Tau is going to be our shear stress, and it's going to counteract the applied stress shear V. All right, from equilibrium. We love equilibrium. We can always go back to it. If we sum forces in the y direction, right, I get a negative V. But I have all of my shear stresses. But shear stress is a stress and it's not a force. So I can't just say plus tau. I need to figure out a force. So I'm going to look at one of these taus and draw a little box around it. And we're going to say that little box has some area, dA, a differential area segment in the cross-section. All right, so if I multiply that little tau times dA, that's going to give me a force. But now I have to add up all those forces in the cross-section. So that's going to be an integral over the area for the cross-section. That'll give me a total force in the cross-section. And then that's going to be an upward force balancing V. The downward force equals 0. All right, so that means that V is going to equal to the area integral of tau dA. Now we want to look at the box into the page. So if I extend the little block into the page, I see I get a little box like this, right? And I'll go ahead and draw this box off to the side. Now when I draw the box over to the side there, I'm going to draw the little shear stress in red on the front face, right? Well, we know if there's a shear stress up on that face, then on the top face, we have to have a balancing shear stress. We learned this when we talked about two-dimensional stresses and plane stress, right? So we have to have a shear stress that looks like the green arrow shown. That arrow is going to balance the red arrow. For equilibrium, this is a requirement. Do not forget this, people. This is very important. So we know for equilibrium of the element, a shear stress forms on the top surface to balance out the cross-sectional surface. Well, that top surface, people, is in the longitudinal direction. Craziness. It's in the direction of dx, or the direction of x in our beam shown above. So that means into the page, I now, not only is my shear causing some sort of problem in the cross-section itself, it's also causing forces to develop in the longitudinal direction. Who would have thought about that? Well, let's see how that stress has to work. And we're going to rely on our old friend equilibrium once again. All right, so if I have this cross-section and I have some sort of moment applied, right? A moment's going to lead me to this bending stress. This bending stress is going to be my over I, right? And I have an equal and opposite one on the other side. I didn't mean to actually join them. I'm going to separate them around, and we'll get them drawn properly here in a second. Alright, so we have this applied bending moment, and that's going to lead to compression on the top face and tension on the bottom face. So I'll represent compression and tension on the cross-sectional face as such. So this is on the left side of that element dx, right? So I have that little wedge dx, and I got compression on the top, tension on the bottom. Well, on the right-hand side, I also have bending moment, right? I've only gone a little bit of distance, so I have a same bending moment, but I do have some sort of differential, plus dm, right? They can't be exactly the same, because as I move along the length, the moment is changing. So I now put in this m plus dm on the right, and I draw the stress profile as such. Again, the neutral axis is situated there. It's a little bit lower towards the bottom because there's more area towards the bottom, so we'd expect the neutral axis to be closer to like the center of gravity of the area. Remember that. So, all right, I have this, and now I'm going to come up with resultant forces, right? This is just like statics. We go back to statics and we do resultant forces. So for a triangle, the resultant force would be about 1/3 from the tall side of the triangle. So I have this resultant force. Now I'm going to call this a differential force, and it's going to be my differential force on the left-hand side, DFL. And then on tension, I have DFL moving to the left. I do the same thing on the right-hand side. I got DFR moving left, and I got DFR to the right. Okay, so I now can sum forces in my cross-section. So summing forces in the x direction, I get DFL to the right minus DFL to the left, plus, minus DFR to the left, and then plus DFR to the right equals 0. Okay, that looks like it's good. DFL minus DFR plus DFR, I think that checks out to 0. All right, so we satisfy equilibrium. We must always satisfy equilibrium, otherwise things are in motion, and in mechanics of materials and our structures and other components and parts, we don't want things moving. We want forces to be balanced. So, all right, we satisfy equilibrium. Now we're going to look at just a portion, right? What if I use the same stress profile above, but I'd look only a portion of the element? So I'm going to cut at that plane that I've drawn with a thickness of t, and I'm going to draw the plane here in a second. Now, when I do that and I consider just a portion, just the top, very top layer of this, I see I have DFL prime and I have DFR prime, right? These are the resultant forces. The resultant force is in green. So here we go. I'm going to get the rest of my geometry shown. I'm going to look at this plane. So imagine I'm slicing that plane, and I'm going to take everything above that plane, and then that's what's shown on the right in that little rectangle, right? So I have just the forces on the top, DFL primed acting to the right, and then I have DFR prime acting to the left. Well, DFL prime and DFR prime were not equal to each other. And so therefore, because they're not equal, if I'm going to some force in the x direction, I need to make sure everything will work. So DFL prime was one value. I'm going to have to add in an extra value for shear acting to the right. And then that's going to help me balance DFR prime. All right, so I know they look scary integrals, but this is just the differential force on the left-hand side and the differential force on the right-hand side. We can continue down through the derivation for this value. I want to draw your attention to that term tau. Tau is a shear stress, right? And that acts over an area. That area, according to our drawing there, that plane is going to be T times dx. All right, so now we need to substitute some variables. We can substitute my over I for sigma. We go through and we start doing some of the integrals, right? We can pull out some of our constants and bring some of the things over to the other sides. We'll have some things cancel. We eventually get down to tau equals dm dx over it times the integral over the area of y dA prime. All right, so then dm dx, we know that the derivative of the moment with respect to x is really the shear. So that gives us now tau equals v over it. Those are all constant values at one cross-section piece. Right? The only thing that changes in the cross-section is the value, the integral over the area of y dA prime. All right, so that's the only thing that we need to include in the integral. Hopefully you remember what this is. This integral is the first moment of the area. It is the value of q. If you go back to statics class, we talked about in statics when we came up with the center of gravity, we had to calculate the first moment of the area. So that was the integral over the area of y dA. Right? So this is something hopefully we should remember. I always tell my students in statics, you're going to have to remember this. So hopefully it comes back, and now we have our equation tau equals VQ over IT. And then this information on the next page is just helping you recall what Q is and how we calculate it in the for centroid. So I've shown here the centroid calculation, and I've shown it as a summation, right? We talk about when we have discrete shapes, when we can break up our shape into discrete components, we can look at it as a summation. The very general form is the area, the integral over the area of y dA over the integral over the area of dA. But we know that whenever we have sections with center of gravities that we can easily identify, we can break it up into smaller sections. Lastly, we have to cover some of the limitations. So remember, we used my over I to come up with this formula, VQ over IT. So all of the assumptions that we used in Euler-Bernoulli beam bending theory still apply, since my over I was used in that derivation, namely that the neutral axis remains the same length, plane sections remain plane, homogeneous material in the linear elastic range. Next, we say the shear stress was assumed to be uniformly distributed over the thickness of the beam. So that is true for most cases, unless we have very weird shapes or very sudden changes in geometry. And finally, the derivation assumes that the resultant shear force is passing through an axis of symmetry in the cross-section. So there's no sort of twisting going on in our cross-section, no warping, none of that stuff. And that is the case for most beams. Most beams and most bars that we come across will be the case that the resultant shear force will be through an axis of symmetry.